I worked in the project last year during an internship at INRIA. It was at Lille, France. And then this year I continued working with the sponsorship of ISUG that I have to thank. And I work with Mariano now. He's my mentor, and he's a developer also. So I will start talking of what is serialization, because I think sometimes it's not clear, or there is not a clean definition of what means. The most common use for serialization, I think, is to share objects to other technologies. So you have an object in Faro, you serialize in some format, and you then deserialize or materialize, like I like to say, in another technology. And for that, you usually lose a bit of precision or a bit of detail on the object. You, for example, serialize a sorted collection, and a sorted collection in Faro points to a block closure that is too difficult to serialize. And so the most common strategy in that case, for example, is to convert or to serialize the sorted collection as a simple array where you preserve the elements order, but in the destination you will not add another element and put it in the correct position. So we are not very interested on that. We are more interested on serialization between similar environments, from Faro to Faro, for example, where we can hope to reproduce the original object with precision, with full detail. And we are also interested on serializing classes in full detail also. We want to serialize a class with the method dictionary and all the compiled methods with full detail. The most the most common strategy for serializing classes is to store just the source code and to compile it in the destination. But we would like to, in future, to serialize the classes in full detail and to deserialize with detail. Okay, now I will speak of some problems and some requirements you have when you serialize. One, in this case, we have an object that that it's unique in its environment. Maradona is unique, and when you serialize Maradona and you reproduce Maradona in the destination environment, you don't want to replicate, to duplicate the unique instance of Maradona that is in the destination already. You want to really serialize a reference to Maradona and to recreate a reference to the unique Maradona. This is a concrete case of that. Is for example, a transcript. If you are serializing a graph that points to transcript, you don't want to serialize transcript with full detail, but you want to serialize a reference, a name transcript, and then your graph in destination will point to the right transcript. There are objects that has not any meaning outside of its environment. For example, a socket or a process. For some of that objects, you really you must exclude them from serialization. Well, another requirement that this is not common on serialization. An object, for example, the sorted collection I mentioned before. The sorted collection may be bit field. In some circumstances, we want to serialize it with full detail and to reproduce the sorted collection with its block closure and all the detail. But maybe in another circumstances, it's better, it's decided to serialize only the array with the elements. So we would like to being able to serialize the same object in two different voids. And another requirement is obviously the classes change along the time. Maybe we serialize it a point with the first version, and then we materialize in an image with another extra variable, and in that case we would like to initialize the value, or maybe there is a variable name change. We would like to let the user to configure, to customize the class change, so that automatically Fuel can materialize the object correctly. And okay. Hello? Oh. Well, now, do you want, I can repeat the, oh, no. Okay, so how to serialize? Our first topic is about human readable formats or binary formats. So in many serializers, there is the requirement to have a human readable format so that the user can open in its text editor the file and look what is the graph, serialize it, or maybe edit something and so edit the graph in that way. That is not what we want. In Fuel, we prefer to have a binary format that is more compact and more fast. So, okay, I will explain two algorithms that are common to serialize. And I have this example, it's a bit confused maybe. I will serialize, I am serializing the first character, the player 1, and each player has a friend and a color. Knows a friend and a color. So player 1 has a friend that is player 2, and it has the color blue. And color blue is represented with a number that is the 255 that represents blue in the system. So this is a graph that we will serialize. Well, in the first algorithm, is the recursive is the most common way of serializing. And here I will explain. We write, starting with by the left, we write, okay, I have an object of class player. And so as player has 2 instance variables, we will next write the 2 objects. So the first object is object of class color that represents the blue. And blue is also has an instance variable that is the value. And the value is encoded as type int, and the value 255. In that case, in the recursion, the int value is like a base case. We stop recursion there. So we then encode the second variable of player 1, that is player 2, and we again object player blah, blah. Then what changes is that when we encode blue, like it is an instance we have referenced before, we will write type is a reference to the second object in the stream. Okay, this is well the recursive algorithm that we did not implement. We prefer to use the pickling algorithm, as we call it, that it basically groups the objects in the graph and then starts to encode it. It is not recursive, it's linear. You first, for example, not for example, we call the groups, the object groups, clusters. So we will write first that we represent our graph with 3 clusters, and then we start. The first cluster is of type object, of class player, and we have 4 instances. Then cluster 2 is for classes, for instances of color. We have 1 instance, and the same for integers. Note that here we describe the graph in a different way. We have like a summary of the instances there. Instead of repeating, I have an object player with an object player, an object player, we just put we have of player, we have 4 instances. Okay, then we encode the references in the second section of the file of the stream, all by indexes. Okay. So well, this is the algorithm we choose. Is the idea is that this way is fastest to materialize than the other, and as we will see later, it's not so slower for serializing. So seems good. Another thing is that some serializers are implemented with some special plugins or implementation at VM level, at virtual machine level, but we want to not use that. We, of course, want to take advantage of plugins that or optimizations that are already in Faro in the system, but we don't want to use special things because it's less portable and the code is less maintainable. Okay, now I will talk about fuel. Well, fuel, I try to define in this slide what are the main characteristics of or requirements or goals of fuel. For the first is concreteness. We want to serialize a graph with full detail, and we don't want to have the trade-off that is needed when you want to be compatible with other technologies. For example, if you want to serialize in Faro and deserialize in Java, you will need to sacrifice the possibility to serialize a sorted collection with full detail, but we don't want that. Well, another thing is flexibility. We would like to not have just one way of serializing an object. We would like to instead to really configure the serializer so that in some circumstances we serialize the full sorted collection, and in other cases we serialize the array. And I really think that we want is to be fast. We make a lot of effort to investigate, to profile, and to obtain a good speed, and of course to have a good design. Okay, so I show here some benchmarks we took with Fuel. This example is serializing a large binary tree. We tried with many. We have a benchmarks suite implemented for doing these metrics, and in general, all the samples are represented in this one. So in blue, you can see the serialization time, and in orange, the materialization. We can see that we are almost at the same level of STOMP and SRP. That's okay, and we are fast materializing. One important thing to note is that the serializers that come with Faro and with Squeak are image segments, marked ref stream, and reference stream. And one objective when we started with Fuel was to have better time of them. And in the last position is Magma, that is really not fair to compare with Magma, because Magma is a framework for persistence that is not just for serialize in the sense we use in Fuel. So okay, I show here that these results are not just for large graph, but we show that with graphs of smaller graphs, the times are the same proportion. Okay. Okay. About the design, I will just say that the white boxes are the classes that the user has to interact with them. They are the facades the user really interacts with. That facades are like builders that build the orange or red boxes, classes, that implement the algorithms, and they know mappers. For example, the mappers are an important element in the design because they provide the flexibility I mentioned to serialize the objects in more than one way, depending on the circumstances. They implement the pattern of chain of responsibility. So when you serialize, you previously configure dynamically what's the strategy for mapping objects, and so you can have the flexibility. These are some metrics of the project. I will just mention that we have almost the same number of lines of code than the lines of test code. We think that's important because we really like to have tests for every feature and to have a good test coverage. You can see the number of lines per method. We try to have small methods with a good design. Okay, I will now show you a demo of one thing we achieved. Okay. ¿Qué pasa? Okay. Okay. Apoyar. Ah, okay. Well, I don't know if you know, Seaside is a project with a large number of classes and of packages, and it took in my machine, for example, took 20 minutes to install it in a clean Faro image. So 20 minutes downloading things and compiling the classes and doing all the stuff. So we prepared like an experiment to capture, to serialize the classes and the packages that are downloaded and compiled during the installation of Seaside in a clean image. We use this script. I will not do this now because as I said, it took like 20 minutes to do it. And I will show the result of the serialization in this case. All this list, every element of this list is a different package that was necessary to install in the image to have Seaside running. Okay? Sure. There are a lot of packages. I will execute now a code that our experiment generates. This code will install Seaside using Fuel. Okay, first I will show the number of classes in the system. This is the number of classes. So, and you can see here in red, this class is in red because Seaside is not installed, so it does not compile. Now I will paste and run it. Now we are materializing in this almost clean Faro image. It just has fuel installed, and after this process is finished, I will show that Seaside is running, okay, and so we saved like 19 minutes of installation. Okay. Now the number of classes changed. Now the command adapter is not read because the class is in the system. I will start the server. You can see that Seaside is not in that port before. Now I will start the server. Okay. Refresh. And the Seaside works. This is to show that the materialized classes are correctly installed and they are working. I can execute the samples of Seaside and everything is okay. And it is running with the classes we materialized. Okay. Well, now it was. Okay, yes, that is another demo I will do. I will serialize an exception, an error, and then materialize it in another image, and I will show that the exception you can continue executing the code. Wait. Let's debug. First, I will debug this code. This code just assigns hello to a variable, a temporal variable. And before following with the execution, I will serialize the debugger. With this debugger all instances first, I will obtain the instance of this window, this debugger. And I will serialize it to a file named debugger.fuel. Okay, now I will show you the file. It's this file. Now I will open another follow. Okay, now I will materialize from the contents of the file, and then I will open the morphic in screen. Okay? Ta-da!
Now to open. Let's see if it works.
Yeah, of course. You can see the variable, the temporal variable is assigned. It changed, and I will show that transcript shows executes the code. So I can do it again if you want. Okay, well, now I will show the second part of the demo. It's a small variant, but I will just insert this line that serializes a context, copy. I will put here that this method executes every time an exception is not catched in far. Paste, accept. Okay. Now I will generate right exception. Do it. Okay. This exception, this zero divide, has been serialized here. That is the error. Okay. Now I will open another follow image. Materialize. That is here. I will materialize the error, or no, the context, and then I will open a debugger with that context. Okay, this is a new debugger window with the same context, and this zero divide exception was raised in another image. Okay. So, well, we have to thank Mariano for this demonstration because he was the author of them. So I will finish the presentation. Feature. A bit of the future. Well, we have to improve the class change management with Fuel because now it's just I will stand up. We have to work in, for example, to provide a way to easily map class change, instance variable name changes. For doing that, for example, we have to improve what I mentioned about flexibility. We have to improve it to. Well, okay, and an open question we have is if we will be able to replace the old serializers that come with Faro. They are image segments, smart ref stream, reference stream, data stream. We would like to be better than them and faster, and so maybe we can replace them in Faro. And we would like to experiment more with package loading to sharing code. to sharing code, to sharing classes with full detail, like I mentioned. We have to work on that. So, well, I finished. The project has received a prize in the ISUG Innovation Technology Awards. Mariano presented the project there, and well, that's all. Question?
It was very impressive to see Seaside loading so fast. But what happens if a superclass changes its shape and it adds a new instance variable? What happens with the methods that are already compiled using a different index for the instance variable?
Yeah. The experiment of Seaside is a bit fragile. It needs everything in the original conditions. We have to work on that, on supporting. And we didn't experiment what happens with the classes already. If Seaside is already in the image or an old version of Seaside is in the image and we install, it should work, but we don't know. We just achieved that, and we have to work more on that. Yeah.
In the regular, not taking into account the package dollar, but if you have a regular option that is serialized, then when you materialize the superclass of that package has added an instance variable, that will be automatically managed by Fuel. The default behavior is to, because we also store the instance variable names, so it doesn't matter the offset, and we can just let that instance variable in here, and there is a hook that we provide, which is you can implement the Fuel after materialization, so that you can implement such method and put something instead of an int.
But the problem is with the already compiled methods that you are loading.
The ones that are already in the image, yes.
That was
yes.
Hi. So I was wondering, are you using something far specific, or I see that you're using code? Does Fuel works with Fuel with the standard image VM?
VM? I think so.
So yes. You're using the code VM and Faro. Does it work with regular script and the standard VM?
With the standard VM, yes, but there's no dependency on the VM at all. With script, in the last version we spent a couple of hours with a file out that we can do to avoid the traits, because script has removed traits in the last version and we use traits for tests. So after a little file out, you can have all tests working without taking into account the serialization and materialization of classes and traits and component methods. The serialization of meta level and classes are not yet working because they are different, but for a regular graph, yes. Absolutely.
Yeah, but I was interested because
For the index, which is another script, so normally it's very slow in a lot of versions, especially if it has some new code. So the Seaside example is really interesting for me. But I don't know if it will work.
More question?
Hi. You mentioned you can serialize objects and also you serialize some of them as references. How do you determine which one are going to be actual serialized objects and which one are going to be referenced? And if you can have a custom way or method when to deserialize the reference, like we have a hook just to serialize something else that is not a class, maybe something that is remote and you want some code to be executed when it's known, when it's being serialized.
Yeah, I mentioned a bit of the hierarchy of mappers in our design. we have a mapper that is called the global mapper, and you pass every object in the graph through the chain of responsibility that implements the mappers. So if you put a mapper at first that says that your object is a global, then you can treat it as a reference. It's okay.
But when you are going to, you have a mapper from going to the object to serialize it. But when you want to materialize it, you have something like an inverse mapper or something like that?
Really, the mapper associates the object with a cluster, a specific cluster. Then when you materialize, you already know what cluster was used to serialize the object. As I showed in the format, you write, you have, in other words, if you treat an object as a global, you will put, for example, in type, global. Number of globals, 4, and then you store the names of that globals. Then when you read the stream, you will read, okay, next I have to recreate some globals, some references, and you read the transcript, and you go to Smalltalk's global, to the system dictionary, to search, to look for it. It's okay? Okay. Thank you.